So now we discuss about electric current inside the conductor. Also, this is also a new concept of drift velocity of electron. So as we know, the conductors generally they are metals and they are the solids. So inside solid, the ions and the atoms are very tightly bound inside, and therefore generally hardly we will get any free ions or free atoms. But still there are few valence electrons, which are free and they move randomly inside. So let's suppose there is this conductor, and inside there are generally 10 power 29 electrons or valence electrons, free electrons per meter cube. In the per meter cube of its cross sectional volume, we get 10 power 29 amount of free electron generally inside the metal. And this free electrons are also called valence electrons. They have a random motion inside, which we also call as thermal velocity, and this is the motion due to the normal room temperature. So normal temperature itself, they shows random motion inside. This free electrons are necessarily the current carriers from one place to another place. So now let's suppose I have n number of electron in a certain place, and each electron, let's imagine they have a velocity vi. This velocity, if I try to do an average, if I try to calculate an average velocity for all the electrons present inside, then I need to do the summation over I equal to 1 to n, which will be the summation of all the velocities for all the n number of electrons divided by the total number of electrons. So this amount would give me the average velocity of all the free electrons present inside. This average velocity generally is found to be 0. Why? Because there is a randomness. Nobody knows that actually how, with what velocity, in which direction these electrons are moving. So when they are moving inside this atoms, inside this material, they always continuously they are into the collision with each other. They are into the collision with another electron or another atom or ion, and therefore continuously they change their direction into a very random way. It's a very random way that they change their velocity, they change their direction. So what happens is generally due to this randomness of their velocity and direction, it has been found that the number of electrons that are moving to a certain direction with a certain velocity, the same number of electrons would be moving to the opposite direction with opposite velocity, and that's how the average, if you take the average of all the velocity for all the electrons, then it comes out to be 0 due to the randomness nature of this motion of these electrons. Now when we talk about providing potential difference between the two ends of this conductor. So when we put a potential difference, let's suppose one is at higher potential and another is at lower potential, and therefore this potential would set up an internal electric field inside. This electric field, due to this electric field, the electrons inside, they would start to feel the force due to this electric field. What would be the force that these charges will feel? Since this charge is an electron, the electronic charge into the electric field, into charge has a negative charge, therefore this amount of force these electrons would feel after the electric field has set up inside. Due to this force, the electrons would also have certain amount of acceleration. This acceleration we can calculate. We know that acceleration is force per mass, which is nothing but E by m. So this amount of acceleration would these electrons would feel when this electric field is set up inside. Now when I try to calculate the velocity of these electrons, we know the velocity of each electron would be their, we already know, would be their initial velocity plus a into t, right? So the initial velocity would be nothing but the average velocity that it was already having, I equal to 1 to n, the summation over I equal to 1 to n divided by n. So this would be their initial velocity. And now since I already know the acceleration, this is E by m into t. So now this is the velocity of the electron. Suppose certain ith electron. This is the velocity of the electron after a time t when the electric field has set up. As we already know, this velocity is generally turns out to be 0 for all the electron. The average velocity turns out to be 0 for all the average velocity for all the electrons inside. Now when we look at a particular situation, suppose between the electrons as it tries to move from inside that material, it comes across the electric field, and due to this electric field, what happens is it starts gaining its acceleration. If there is a acceleration, and due to the acceleration, what happens, it starts to gain certain certain kinetic energy. Now as it starts to gain certain kinetic energy and it starts to move, what happens, it comes across another particle or another atom or another electron, and it gets collide and it moves to another certain direction with another certain random direction and another certain random velocity. And generally what we do between two collisions, suppose there is one collision here and another collision here, between two successive collision, let's suppose it has spent, without any collision, it has spent certain time called tau. This time is called as relaxation time. And in this time, suppose it has a velocity vd. This is the amount of the velocity that the electron is supposed to actually have moved against the electric field. So when we calculate this amount of velocity, which we also call it as drift velocity, as we know, this drift velocity we need to calculate for the time which is a relaxation time, which is a time between two successive collision that a particular electron has faced. So therefore we can tell that v, or this drift velocity vd, is nothing but, because it turns out to be 0, and this e by m, and the time taken for it is the time tau. So this is the amount which is given by the drift, or which is the expression for the drift velocity for a time tau that it has moved scattered or uncollided between two successive collision. This is the path it has moved, and this is the time it has taken, which is called relaxation time, and this is the velocity which it has actually drifted towards the positive side against the electric field. So if the electric field is positive to the negative direction, then the drift of the electron is in a negative direction of electric field, which is towards the positive side of the charge. So and the amount is given by E tau by m. Now if I have to draw a very simple diagram, suppose without an electric field, it was moving a certain direction like this. The electric field direction is E, so it would move from A to B. Suppose if the electric field direction is this, then what we see is there is a shift, now B dash. So against or opposite direction of electric field, the path and the velocity has moved or shifted towards or drifted towards the opposite direction of the electric field for the electron once the electric field has started. So that's how the electrons, which we know would move from negative place to the positive direction. So as we see this, due to this electric field, there is a drift or there is a shift in the electrons towards this direction. Now coming to another concept which is very similar to the drift velocity. So drift velocity per electric field is what we call it as the mobility of the electron, which is denoted by the letter mu. And as we know, the drift velocity would tell us how much electron has drifted towards this positive direction. Mobility also tells us how much the drift velocity would be for a certain electric field, which is given by the letter mu, and this, the expression of it is E tau by m. So this is the term called mobility of the electron, which gives the drift velocity of the electron for a certain electric field.